So here we're going to use the same example, and we're going to show how to determine the gain margin here. Again, the gain margin is defined by here, that is the gain margin. The gain margin is calculated when the phase angle is 180 degrees. That means you can see measure from here to here corresponding to this point. Right? So here we solve for omega CP by using this one. We simply set which occurs, which is equal to the magnitude of the GS when S equal to J omega C, the crossover frequency, the phase crossover frequencies. Okay, and how to determine this one? Omega CP can be determined by, again, using these definitions. So we calculate the gain margin. The gain margin is corresponding to this frequency. This frequency is corresponding, the angle is 180 degrees minus. So that is by when this angle equal to minus 180 degrees, that happened at S equal to J, the phase cross over frequencies. Be good? So we determine this one using this. Okay. So for this case, we can then we can need a little bit more calculations. So we can copy from here. So where the GS, simply let me repeat the calculation: 0 degrees. The G equal to this one. The GS equal to K and S plus 1, S plus 5. So therefore the G, the J omega will be equal to 0 degrees on the numerators minus this J omega due to this term, the first one, plus the J omega plus 1, the second term, plus the J omega plus 5 for the third term. So this one basically 0 degrees minus this is 90 degrees. Okay, this one is arctangent omega. This is arctangent omega over 5. Okay, and so here basically here I want to utilize introduce you one equation here. We have to combine these in algebra. So usually we have this formula arctangent, say x plus arctangent y, and we have the formula is arctangent x plus y and y minus xy. Okay. Using this equation, we can combine into the single one. So, and I believe you have to use this equation in homework and might use it in the test. Okay. Don't worry, if we're going to have the test like this one, I will provide this to you again. So basically this is minus 90 degrees minus arctangent. So apply that one is 6 over 5 omega and 1 minus omega squared over 5. Okay, so that's arctangent. Okay, so right now we are looking for this one. So simply at omega CP minus 180 degrees equal to this angle G J omega, and that one equal to minus 90 degrees minus arctangent 6 over 5 omega 1 minus omega squared over 5. Okay, so using these equations, and we can solve for omega. So therefore omega CG CP will be equal to square over 5. That is 2.21 radians per second. You good? Okay. So once we have this one, you simply plug it back to here. So therefore, the magnitude, you can calculate that one as equal to J at J 2.21. You can determine its magnitude, and its magnitude basically again that is K and S plus 1 and S plus 5 again when S equal to J 2.21. Okay, so let me borrow a little bit space here. We're running out of space. So again, let me copy that one to here. So G at S equal to J at the 2.21, and that one we have say when K equal to 10 and when K equal to 100. Okay, we simply plug in do the scenario study when K equal to 2 possible values, then its magnitude can be easily determined. So that is equal to 3. Let me get more space. So G as the magnitude at S equal to J omega Cp, and that means equal to J 2.21. That has two values, and one is equal to 3 for K equal to 10. It has the value equal to 0.3 when K equal to 100. Okay, so that's the magnitude and be determined using these equations. And of course here you need a little bit more kind of the calculation by punching calculators. Okay, so then we do the calculation for K to 2 possible values for this one. And if you like to convert it into dB, decibel, that can be equal to 9.5 dB. This one can be equal to minus 10.5 dB. But anyhow, and what we need is the two numbers here. What we need is the magnitude 3 and 0.3. So therefore the gain margin will be equal to, I'm kind of going over too quickly. Allow me to modify the numbers. Okay. This one equal to 1.3. This one equal to 1.1 divided by 0.3. Okay, sorry. So that's for K to 10. So for the gain margin, basically the gain margin by definition is 1. Again, we simply, right now you have this one. So gain margin by definition is the scale, the ratio between 1 to the magnitude of the G. Okay, so divide by the magnitude of the G, and J at J equal to J 2.21. Okay, so simply this one equal to 3, and for K equal to 10, and this is 0.3 for K equal to 100. And this way you can convert into decibel. Okay. So on the body plot, the first scenario basically indicating that is the curve. The body plot at that point is below the 0 dB for K equal to 10, which means a stable system. And for these systems, basically the body plot corresponding will be something like this. At this frequency, the magnitude of the body plot is above. That one, this case corresponding is this one. Okay, so that is for unstable system. Again, from the previous, the phase margin, you can also tell when for the scenario k equal to 100, that corresponding is negative phase margin. That is unstable system. Let me make the final comments. And if you like to use the MATLAB to do the calculations, so for this case, you can using is this. Transfer functions will be equal to numerator equal to k, and you can set it up the k parametric, say for example k equal to 10, or later on you can change k equal to 100. Just change the values, and then we define the systems, and this one equal to 1650. Okay, that is the numerator denominators here. And then you can define the plot, and for the omega, you can define it called the log space. Okay, log space you can say from 10 to the minus 1 to 10 to the 2 or 1, whatever, and you give the 15 points of the calculations. Okay, then you can use this command, and using margin. I think. Sorry, this is the transfer functions, and this is our system. Sorry, okay? So this is our system. So once you use margins, this command, then the MATLAB will give you a body plot with, in addition to the body plot, then on the top, MATLAB will give a note, will give you the note saying the phase margin is how much, gain margin is how much. So basically, MATLAB will do the calculation for you. Give a try. Yes?
Should omega be part of margin?
This is a margin.
Right, but the log space.
Yes. Yeah. So this one, it seems I hear this didn't use it, but never mind. Okay. You can try. I forgot, but at least you can just type it.
It's probably in the documentation.
Yeah. So since this is redundant, I would say this is redundant. Okay. Give it a try.
It's probably in the documentation how you can include log space.
Yeah. Or otherwise, the other possible command you can have the MATLAB to output the value for you. So basically, here is this gain margin. The arrangement is in the sequence. Okay, follow this syntax, and phase margin. And this is the omega CG and omega CP. And you have MATLAB to output the 4 quantities for you, and using this command, the margins, M-A-R-G-I-N. And system. Okay. And if you would type using the second command, I believe the MATLAB won't plot the graph for you, but rather than will give you the 4 numbers output. So up to you, okay? And with those things, and also remind, and this one is, in MATLAB, its output is only the pure magnitude, okay? It's only pure magnitude. If you like to convert it into dB, then basically 20 times log GN, that is going to help you to convert the magnitude into decimal. Keep this in mind, and that is a special, the MATLAB output is simply a pure number, it's not in decimal. Be good? Okay, so I think that's it for this.